You are looking at a map of the universe, and there is something in it that should not be there. James Webb aimed its mirror into the deep dark and found a structure so wide that our best theories snap trying to measure it, billions of light years across, older than it has any right to be. Tonight, we travel to a galaxy that grew up too fast, a ring of matter bigger than any law allows, and a web of light stretching back to the dawn of time. Each stop is stranger than the last. Scientists spent whole careers building rules for how big things can get, and this discovery breaks those rules in half. If cosmic mysteries keep you up at night, hit like and subscribe so you never miss the next journey. Buckle in, we begin. Look up on a clear night, and space looks scattered, stars tossed around like spilled salt on a black table. That picture is a trick. Every star you see, and the trillions you cannot, hangs inside one single connected shape that spans everything. Scientists named it the cosmic web. Imagine a spider web soaked in morning dew. Thin threads cross other threads. Tiny drops cling wherever the strands meet. Now grow that web in your mind until each dewdrop becomes an entire galaxy packed with hundreds of billions of suns. That is the true shape of the universe at its largest scale. Galaxies almost never float alone. They line up along invisible bridges of gas and dark matter called filaments, strung together like beads on a necklace that runs for hundreds of millions of light years. Where many filaments cross, galaxies pile into dense knots, the busiest cities in all of creation. Between those bridges sit the voids, gigantic empty rooms where almost nothing lives. A single void can stretch so far that light takes 100 million years just to cross it, and inside, you could travel your whole life and never pass a single star. This web is staggering. It reaches across the entire observable universe, a span of about 93 billion light years, so wide that light itself has never had time to travel from one edge to the other since the beginning of time. For most of human history, nobody knew it was there. We saw single stars, then single galaxies, then small clusters. The full pattern stayed hidden, like trying to guess the shape of a forest while standing with your nose pressed against one tree. Astronomers suspected the web existed because their math demanded it. Gravity pulls matter together over billions of years, and the faint ripples left over from the young universe should grow into exactly this kind of lace. Proving it was the hard part. To map the web, you have to see galaxies so far away that their light is fainter than a candle on the moon, older than the Earth, older than the sun, reaching back toward the first morning of everything. Ordinary telescopes hit a wall. The light from those first galaxies is not only dim, it has been stretched and reddened by the expanding universe until it slides out of the range human eyes and normal cameras can catch. For decades, that faraway region stayed a smear of shadow. We knew something enormous waited out there. We simply could not see its real form. Then a machine the size of a tennis court unfolded a golden mirror 1,000,000 miles from Earth and turned its gaze into the oldest, darkest corner of the sky. What it sent home did far more than sharpen the smear. It revealed a structure so large that the people who study the universe for a living are still arguing about whether their own theories can survive the sight of it. Before we reach that structure, you need to understand one thing. Why did this single telescope win where every other eye in history failed? How did it learn to see what light itself had tried to hide? The answer sits in a color your eyes have never seen. That color is infrared, and it is the reason James Webb changed everything. Your eyes catch only a thin slice of light, the rainbow from red to violet. Infrared sits just past red, a kind of glow you feel as heat but never see. Reach your hand toward a warm stove without touching it. That warmth on your skin is infrared, pouring off the metal in waves too long for your eyes to notice. Here is why that matters for the deep universe. As space expands, it stretches the light traveling through it, the same way a drawing on a balloon stretches wider as you blow it up. Light that left a young galaxy as ordinary visible glow gets pulled longer and longer during its billions of years of travel. By the time it reaches us, It has slid out of visible light entirely and turned into infrared. To older telescopes, those first galaxies were simply gone. Their light shifted into a band those machines were blind to. James Webb was built for exactly this glow. Its golden mirror, wider than a giraffe is tall, gathers infrared with almost impossible sensitivity. Think of it as the finest night vision goggles ever made, able to spot the faint heat of a bumblebee at the distance of the moon. That is not an exaggeration handed out for drama. Engineers tested and confirmed it before launch. Infrared has a second gift. It slips through dust. Space is full of thick clouds of it, and visible light crashes into those clouds and scatters, leaving whole regions hidden behind a grey curtain. Infrared passes through the curtain the way heat from a campfire reaches you even when smoke hides the flames. Places that looked like empty black nothing to earlier telescopes suddenly filled with newborn stars and half-formed galaxies once Webb looked with infrared eyes. To make all this work, the telescope had to stay colder than almost anywhere in nature. Heat is infrared, so a warm telescope would blind itself with its own glow, like trying to photograph a candle while your camera is on fire. Engineers wrapped Webb in a sunshield the size of a tennis court, 5 paper-thin layers that drop the temperature to more than 390 degrees below zero on the Fahrenheit scale. Only in that deep chill can it sense the whisper of light from the beginning of time. Then came the hardest part. They flew it 1,000,000 miles from Earth, 4 times farther than the moon, to a quiet point in space where it could stare without our planet or sun ruining the view. There it unfolded on its own, mirror segment by mirror segment, with no chance of repair if anything jammed. Every step worked. The result is a telescope that sees the young universe not as a rumor, but as a photograph. Galaxies that were pure guesswork became sharp images. Colors nobody had ever recorded streamed into its detectors night after night. And once astronomers had this new eye, they aimed it at one patch of sky and left it there, night after night, gathering light for a project so ambitious it would map more galaxies at once than anyone had ever attempted. What that single patch revealed is where the trouble begins. The project had a plain name, Cosmos Webb, and a wild goal: to photograph one window of sky so deeply that the entire skeleton of the universe would show through. Astronomers pointed James Webb at a single region and returned to it again and again, letting the faint light pile up like rain filling a bucket drop by drop. When they finally stitched the images together, they held the largest and deepest map of cosmic structure ever built. The numbers behind it are hard to hold in your head. The survey captured nearly 800,000 galaxies in one field of view. Each dot of light in that image is not a star. Each one is an entire galaxy, a swirling city of tens or hundreds of billions of suns. Line them up and you are looking at more galaxies in a single picture than there are people in most countries on Earth. The map does something no earlier picture could. It reaches back in time. Because light takes so long to travel, looking far into space is the same as looking into the past. The nearest galaxies in the image show the universe as it is now. The faintest, reddest specks show it as a toddler, barely 1 billion years past its birth. In one frame, you can slide your eye from the present day all the way to the ancient dawn, like reading a family album that starts with a wrinkled grandparent and ends with a baby photo. And there, spread across that map, the cosmic web finally revealed its shape in full. The filaments were real, glowing threads of galaxies running for hundreds of millions of light years. The knots were real, packed clusters blazing where the threads collided. The voids yawned between them, dark and vast. For the first time, humans could see the architecture of everything laid out like a blueprint, confirmed with their own instruments, instead of trusted on faith. One researcher on the team put it simply: James Webb had completely changed our view of the universe. That was not a boast. Before this map, the web was a shape drawn mostly in computer simulations. Now, it was a photograph, matching the predictions so well that scientists could measure the strands and weigh the clusters strung along them. Yet the very success of the map opened a door nobody wanted to walk through. When you can finally see structure clearly, you can also see when structure gets too big. And as astronomers traced the Webb out to its grandest scale, expecting it to smooth into an even, uniform haze, they kept catching shapes that refused to smooth out, curves and rings and walls that stretched on far past the size any structure is allowed to reach. To understand why that is terrifying to a cosmologist, and not just surprising, you have to know the single most important rule the entire science of the universe is built upon. It is a rule so basic that most people have never heard of it, yet nearly every theory about space, time, and the fate of everything quietly depends on it being true. Break that rule, and the foundation under modern cosmology starts to crack. And the structures in this map may be doing exactly that. The rule has a grand name, the cosmological principle, and a simple heart. It says that if you zoom out far enough, the universe looks the same everywhere and in every direction. No special corners, no privileged center, no giant lumps in one place and nothing in another. On the largest scale, matter should be spread out smoothly, like sugar stirred evenly through a glass of tea. This idea grew from a long lesson in humility. People once believed Earth sat at the center of creation. Then we learned Earth circles the sun. Then we learned the sun is one ordinary star among hundreds of billions in our galaxy, parked in the quiet suburbs, nowhere near the middle. Then we learned our galaxy is one among trillions. Each discovery pushed us further from any throne. The cosmological principle takes that lesson to its end. We are nowhere special, and the patch of universe we can see is a fair sample of the whole thing. Now, up close, the universe is obviously lumpy. Planets clump, stars clump, galaxies clump into clusters. Look at any small region, and matter is scattered wildly, thick here, empty there. The principle does not deny that. It says the lumpiness has a limit. Zoom out past a certain size, and all those clumps should blur together into a smooth, even spread, the way a beach looks like a solid tan blanket from an airplane, even though it is made of countless separate grains of sand. Picture stirring milk into coffee. At first, there are swirls and streaks, pale clouds twisting through the dark. Keep stirring, and the streaks vanish, leaving one even color throughout the cup. The cosmological principle promises that the universe, viewed on a large enough scale, has already been stirred smooth. There should be no swirl left that is too big to blend in. This is not a small side note. It is the second most important assumption in all of cosmology, sitting just behind Einstein's theory of gravity. One physicist described what would happen without it in blunt terms. Without smoothness, he said, all order would break loose. Nearly every calculation about how the universe expands, how old it is, how it will end, quietly assumes matter is spread evenly at the grandest scale. Pull that assumption out, and the equations that describe the fate of everything stop working the way we think they do. So the principle also sets a size limit. There is a scale beyond which nothing is supposed to stand out. Above that size, a group of galaxies here should look no different from a group of galaxies there. If you find a single structure larger than that limit, something is deeply wrong. Either you got unlucky and stumbled on a freak, or one of the safest assumptions in science is broken. For a long time, this stayed comfortable and untested. Telescopes could not see far enough to check the largest scales, so the smoothness was taken on trust. It worked in the math, so it must be true in the sky. Then the maps got deeper, the surveys got wider, and astronomers finally reached the size where the universe was supposed to go perfectly smooth. That is exactly where they found something that should not have been possible. To feel why it shook them, you first need the actual number, the exact size past which nothing is allowed to grow. That number is roughly 1.25 billion light-years. Above that span, according to the standard model, no single structure should exist. Groups of galaxies can stretch a little, walls can wander, filaments can run long. Past that ceiling, though, the universe is supposed to blur into an even haze with nothing standing apart from anything else. Hold that size in your mind, because it is almost impossible to feel. A single light year is nearly 6 trillion miles. Light, the fastest thing there is, circles the Earth more than 7 times in 1 second, yet it takes over 4 years just to reach the nearest star beyond the Sun. Now stretch that journey to 1.25 billion years of non-stop travel at the speed of light. That is the ceiling. That is the largest anything is allowed to be. Where does the ceiling come from? It falls straight out of the cosmological principle. Scientists calculated the point at which the lumpiness of the universe should finish smoothing out. Below that scale, you can still spot clumps and gaps. Above it, any patch of sky should be a perfect twin of any other, evenly filled, no surprises. They ran the math carefully. The transition to smoothness lands right around that 1.25 billion light-year mark. Think of it as a cosmic speed limit, though instead of capping how fast you drive, it caps how big anything can grow. The rule is not a suggestion. It is baked into the equations that describe how matter gathered after the universe was born. In the beginning, there were only faint ripples, tiny regions slightly denser than their surroundings. Gravity spent billions of years pulling matter into those denser spots, building filaments and clusters. There was only so much time, and gravity works only so fast, so there is a hard limit on how large a connected structure can assemble. Reach past that and gravity simply has not had enough time since the Big Bang to build something that big. That last point is the heart of the problem. The size limit is really a time limit in disguise. The universe is about 13.5 billion years old. Gravity has had that long and no longer to sculpt everything we see. To build a structure larger than the ceiling, gravity would need more time than the universe has existed. It would be like finding a tree taller than any tree could grow in the years since the seed was planted. The tree itself would prove that something about your story of its growth is wrong. So the ceiling is a promise and a test at the same time. It promises the universe is smooth on the grandest scale. It tests every deep map we make. Find nothing bigger than the limit, and the standard model stands strong. Find something bigger, and you have caught the universe breaking its own most trusted rule. For decades, no map reached far enough to run the test honestly. The ceiling stayed a safe piece of theory, never truly challenged. Then surveys pushed deeper into space than ever before, right up to the scale where smoothness was supposed to rule. The first thing they found out there was a wall of galaxies so long it made astronomers look twice, then a third time, wondering if their instruments had lied. The first crack in the ceiling came in the shape of walls. Not walls of brick or stone, but walls of galaxies. Thousands of them, lined up in a vast flat sheet stretched across the darkness. The most famous early one earned a fittingly huge name, the Sloan Great Wall, and it ran for more than 1 billion light-years from end to end. When astronomers first traced its length, it stood as one of the largest things ever seen, brushing right up against the size the universe was supposed to forbid. A wall like that is hard to picture, so try this. Imagine every galaxy as a single grain of sand. Scatter those grains at random across a beach and you get an even boring spread. Now imagine that instead of scattering evenly, a huge share of the grains lined up into one long ridge, running the entire length of the shore, standing out sharply from the smooth sand around it. That ridge should not form on its own if the beach is truly even. The Sloan Great Wall is that ridge written across the sky in galaxies. For a while, astronomers told themselves these walls were flukes, or that careful measurement would shrink them down below the ceiling once the boundaries were pinned exactly. Structures far away are fuzzy at the edges, and it is genuinely tricky to say where one ends and empty space begins. Maybe the walls only looked oversized. Maybe better data would tame them. Better data did the opposite. As surveys mapped more sky and pinned down more galaxy distances, the giant structures did not shrink. New ones appeared, and some dwarfed the walls that came before. Each discovery chipped a little more confidence off the idea that the universe smooths out neatly at the ceiling. Here is what made the walls so unsettling. A single oversized structure could be shrugged off as bad luck. In a universe this enormous, one freak might slip through by pure chance, the way one person somewhere will win a lottery even though no single ticket should. Scientists could live with one freak. What they could not easily explain was a pattern of them, one giant after another, each supposedly too rare to happen, all showing up in the same sky. The walls also raised a sharper question. If gravity had only so much time to build structures, how did it assemble something a billion light-years across at all? These sheets were not loose scatterings. They were coherent, organized, the galaxies clearly gathered along shared lines. Something had herded them into place across distances so vast that light itself needed a billion years to cross from one side to the other. Astronomers began to suspect the walls were only the beginning. If structures this large were real and not measuring mistakes, then deeper surveys, reaching farther and fainter, might uncover shapes even more extreme. The ceiling had been treated as a solid roof. The walls suggested it might be more like a ceiling in an old house, already showing the first hairline cracks that hint at something heavier pressing down from above. Then a young researcher, sifting through the light of distant blazing galaxies, noticed something that did not look like a wall at all. It curved. It bent across the sky in a smooth, sweeping arc, far too long and far too neat to be an accident. The curve she found became known as the giant arc, and its size is where the polite disagreement turns into open alarm. This structure of galaxy clusters sweeps across the sky in a graceful bow, and end to end it stretches about 3.3 billion light-years. Set that against the ceiling of 1.25 billion, and the arc is nearly 3 times too big. It has no business existing. Picture the sky as a vast, dark dome above you. Now imagine a faint smile of galaxies arcing across it, so wide that if your eyes could see it directly, it would span an area of sky as broad as many full moons lined up side by side. It is not a random smear. It bends with a clear, sweeping shape, the galaxies following a curve as if drawn by an invisible hand. That shape is the truly disturbing part. A messy blob might be excused as bad luck, a chance pileup of galaxies that happen to land near one another. The arc is organized. Its clusters trace a smooth line across an unthinkable distance. Whatever gathered them did so with a kind of order. Herding matter into a single bending form across a span light needs more than 3 billion years to travel. Remember, the size limit is really a time limit. Gravity has had about 13.5 billion years to build everything in the universe, and it works only so fast. To assemble a coherent structure 3.3 billion light-years long, gravity would need far more time than it has had, or some force we do not understand gave it a shortcut. The arc is like finding a sandcastle taller than the tide could ever build in the hours the beach has existed. The castle itself argues that your story of how it formed is missing something. The astronomer who found it framed the stakes plainly. The cosmological principle assumes the part of the universe we can see is a fair sample of the whole. Matter should be spread evenly on the grandest scale, with no lumps above the ceiling. The giant arc is a lump far above the ceiling. From the standard theories, she noted, structures on this scale were not thought possible. You might expect one freakishly large object in the entire observable universe, if you were unlucky. Finding a clean, curving giant almost 3 times over the limit is a different kind of trouble. And the arc did not arrive alone into an empty debate. It joined a small but growing family of oversized structures, each one supposedly too rare to exist, all crowding into the same universe. One giant is a fluke. A collection of giants starts to look like a message. Either the cosmos keeps winning impossible lotteries, or the rule that says these things cannot form is simply wrong. The arc set off a hunt. If a structure this large was hiding in the data, waiting to be noticed, what else had we missed? Astronomers went back to their maps with sharper eyes, searching the deep sky for more shapes that broke the ceiling. But before we follow that hunt, there is a mystery worth pausing on. How do you even find a curve of galaxy clusters billions of light years away, most of them far too faint to photograph directly? The answer is a clever trick that reads shapes written in stolen light. The trick is to hunt structures you cannot see by using light that passes straight through them. To pull it off, astronomers borrow the brightest beacons in the universe, quasars. A quasar is a distant galaxy with a monster black hole feeding at its heart, and the swirling matter around that black hole blazes so fiercely it can outshine every star in the galaxy combined. From billions of light years away, a quasar works like a lighthouse lamp shining across an ocean of darkness. Now comes the clever part. When light from a faraway quasar travels toward Earth, it has to pass through everything lying between here and there, including the cool gas that surrounds distant galaxies. That gas is invisible on its own, far too faint to photograph, but it is not passive. As the quasar's light streams through, the gas drinks in certain exact colors, swallowing thin slivers out of the beam, the way a stained glass window blocks particular shades of sunlight. By the time that light reaches our telescopes, it carries dark gaps in its rainbow, like missing teeth in a comb. Each gap is a fingerprint. Different elements swallow different colors, so a gap in one spot means iron floated in the beam's path, a gap in another means magnesium, and so on. Reading those gaps is like scanning a barcode at a checkout counter. The pattern tells you exactly what the light passed through and roughly how far away it sat. Do this for one quasar, and you learn about one thin pencil line through the cosmos. The magic comes from doing it for tens of thousands of quasars scattered across the sky, each beam stabbing through a different part of the darkness. Line up all those fingerprints and a hidden map appears. Wherever many beams show gas at the same distance in the same region, you have found matter, even though you never saw a single galaxy glow. It is like mapping a dark forest by shining thousands of flashlight beams through it and noting where each beam catches on a hidden branch. This is exactly how the giant arc revealed itself. The researcher was not staring at a photograph of galaxies. She was studying the fingerprints left in quasar light, thousands of beams shining through one patch of sky. When she plotted where the gas clumped, the dots did not scatter at random. They lined up along a long, smooth curve, the shape emerging out of the numbers like a picture rising out of a dot-to-dot puzzle. That is what makes the discovery both powerful and fragile. Powerful because it uncovers structures otherwise invisible, mapped by their shadows instead of their light. Fragile because the human eye is desperate to find shapes, and a curve drawn from scattered dots invites doubt. Was the arc a real object, or a pattern our pattern-hungry brains stitched from noise? That question would haunt the whole debate, and we will return to it. For now, the trick worked. And it kept working, because the same researcher, reading the same kind of stolen light in the same crowded corner of the sky, soon noticed a second shape near the first. This one was not a curve at all. It was a ring, closed and round, and its near-perfect form would prove even harder to explain away. The ring she found is called the Big Ring, and its shape is what makes it so hard to dismiss. It is a closed loop of galaxies and galaxy clusters, round and complete, sitting in the same crowded region of sky as the giant arc. Across its face it measures about 1 1/3 billion light-years. Trace its full circumference, all the way around, and you cover roughly 4 billion light-years of galaxies, strung into a single circle. A curve can be argued away as a chance alignment. A closed ring is far stranger. To build a curve, you only need matter to happen to line up along a bending path. To build a ring, matter has to come back and meet itself, closing the loop on every side. Nature does not casually draw perfect circles. A billion light-years wide, there is no simple force that herds galaxies into a giant hoop across a distance light needs over 1 billion years to cross. Try to hold the scale of it. If you could pin the Big Ring against the night sky and see it with your own eyes, it would span an area about 15 full moons across. 15 moons, laid edge to edge in a great circle. every point along that circle marking not a single star but whole galaxies packed with billions of suns. Standing under it, you would be looking at a piece of the universe so large that your mind has no honest way to picture it. The Big Ring did not just tie the record for oversized structures. It shattered the comfort that the giant arc might be a lonely freak. Now, there were two colossal, organized shapes, both far past the ceiling, both crowded into the same neighborhood of the sky, practically cosmic neighbors. The researcher pointed out how bizarre that is. In a smooth universe, you might expect, at most, a single exceedingly large structure in all of observable space, and only if you were unlucky. Finding two giants side by side is like flipping a coin and getting 100 heads in a row, then walking to the next room and doing it again. There is no known cause for the Big Ring within our current understanding of the universe. That is the plain, uncomfortable summary. Scientists can measure it. They can map its shape from the fingerprints in quasar light. What they cannot do is explain how it formed. No standard process in the accepted model builds a closed ring on this scale. It stands as one of the largest structures ever found, and one of the least understood. It also arrived as roughly the seventh giant structure discovered that seems to defy the rule of smooth, evenly spread matter. 7, each one supposedly a once-in-a-universe rarity. Yet here they are, piling up in our maps one after another. A single anomaly can be luck. A crowd of them starts to feel like the universe is trying to tell us the rulebook is wrong. The more astronomers stared at this ring, the odder it looked. Its orientation seemed almost deliberate, its face turned toward us as if posed for a portrait. That detail bothered them, because it hinted the ring might be even more special than a random giant, or that we were being fooled in a very particular way. Why would a structure 1 billion light-years wide appear to face Earth directly? That strange coincidence points to something unsettling about how we found it. Here is the detail that raises the hair on the back of a cosmologist's neck. The Big Ring does not sit at some random tilt in space. It appears to face Earth almost head-on, its full circle turned toward us like a target lined up in our sights. Of all the ways a ring could be angled in 3-dimensional space, it presents us with the clearest possible view of its shape. That should feel suspicious, and it does, in 2 very different directions. One reading is thrilling, the other is deflating. Both matter, and honest scientists hold both at once. Start with the deflating one, because good science tries hardest to kill its own exciting ideas. A ring only looks like a clean ring if you happen to view it face on. Tilt a hoop away from you, and it flattens into a thin oval, then a line, then almost nothing. So think about how these structures get discovered. We find them by reading the fingerprints in quasar light, spotting where gas clumps along our line of sight. A ring turned face toward us spreads its matter across a wide patch of sky at nearly the same distance, which makes it stand out beautifully in the data. A ring turned edge on would smear into a stripe we might never recognize as a ring at all. In other words, we may be finding face-on rings precisely because those are the only ones we can see clearly. Countless tilted rings could hang in the sky, invisible to our method, while the rare face-on ones jump out and grab our attention. The researcher who found it noted this herself. The ring's orientation is likely not a coincidence, but the very reason it was findable from Earth in the first place. That is a humbling thought. The universe might be full of these shapes, and we notice only the ones posed conveniently for our cameras. Now the thrilling reading. What if the face-on orientation is real, and not just a trick of what we can detect? Then we are looking at something genuinely aimed at us, and that raises deep questions about how such a structure formed and why it would greet us so squarely. Some researchers wonder whether these giant rings connect to features baked into the universe at its very birth, patterns from the first instance that could leave marks with special shapes and directions. If so, the orientation is a clue, not a bias, pointing back toward physics we barely understand. The tension between these 2 readings is the whole game of cosmology. In a nutshell, every extraordinary discovery must survive a brutal question. Is this a real feature of the universe, or a shadow cast by the limits of how we look? A ring facing Earth is exactly the kind of finding that could be either a profound signal or a comfortable illusion, and telling them apart is fiendishly hard. The researcher and her team pushed to settle it. They studied the ring more carefully, mapping not just its outline, but its structure in depth, trying to learn whether it truly was a simple flat hoop turned our way. What they uncovered did not simplify the picture. It made the ring stranger still, because the big ring, it turned out, was never really a ring at all. When the team looked closer, the flat hoop unwound into something with a twist. The big ring is not a simple circle lying face-on in space. It is a coil, a shape that winds around and around, more like a spring than a wedding band. Seen from Earth, it fooled us into reading it as a flat ring, but its true form corkscrews through 3 dimensions. Picture a slinky, that toy metal spring that walks downstairs. Look at a slinky straight down its length, peering into the open end, and the coils stack up into what looks like a single flat circle. You cannot see the winding. Only when you tilt it do the loops separate and reveal that the circle was actually a spiral all along. The big ring appears to be doing the same thing to us. Turned toward Earth, its coils overlap into a ring-shaped shadow, hiding the corkscrew underneath. This makes an already impossible object even harder to explain. A flat ring was strange enough. A coil demands even more organization, more structure, more of whatever force gathered this matter into a shape across 1 billion light-years. Nature builds spirals in some places, like the arms of galaxies or the twist of a seashell, but those are tiny compared to this, shaped by forces we understand. A corkscrew of galaxies, billions of light-years long, has no easy home in the standard story of how structure forms, and there is more crowding into this single patch of sky. The giant arc and the big ring sit as cosmic neighbors, close together in the same distant region. Astronomers began to suspect the two might be linked, pieces of one even larger arrangement rather than separate oddities that happened to land near each other. A filament of galaxies could stretch between them, tying the curve and the coil into a shared design. If that is true, the thing we are dealing with is not 2 record-breaking structures. It is one superstructure, larger than either piece alone, and even further beyond the ceiling. Sit with what that means. We started with a size limit of 1.25 billion light-years, the point past which the universe was supposed to smooth out. Then came walls brushing that limit. Then the giant arc, nearly 3 times over. Then the big ring, a closed loop where no loop should form. Now, the ring reveals itself as a coil, and the coil and the arc may be joined into something grander still. Each discovery has pushed the trouble further, and none of it fits the rulebook. The researcher summed up the growing weight of it. The big ring challenges the principle of smoothness, just as the giant arc did before it. And if the ring and the arc together form a single, still larger structure, then the challenge to that principle becomes far more serious. 2 giants are hard to dismiss. One combined giant, larger than either, in a place the universe promised would be smooth, is nearly impossible to wave away. The hunt was not finished. The same tireless researcher kept looking, and what she reported next did more than add another oddity to the list. It threatened to swallow the arc and the ring both into a single monster, the largest of them all. The newest giant is called the Giant Ring, and it may be the one that ties everything together into a single, unbelievable whole. Reported only recently, this structure appears to join the giant arc and the big ring into one connected arrangement, an enormous ellipse of matter spanning more than 3 billion light-years across the sky. If the arc and the ring were troubling on their own, this stitches them into a monster far larger than either. The way it emerged is a story of pattern upon pattern. First, there was the giant arc, a single sweeping curve. Then the researchers spotted a second curve nearby, a kind of matching arc on the other side. Fit a smooth oval through both curves, and the 2 arcs became the top and bottom of one vast ellipse. That fitted ellipse turned out to wrap almost perfectly around the big ring, which had been discovered separately in the same crowded region. Two great shapes, found by different clues, folding into one nested design. Try to picture it. Imagine two enormous rings hanging in the same corner of space, not quite lined up, one tucked inside the frame of the other, both turned roughly toward Earth. From our viewpoint, they overlap into a dizzying set of loops within loops, like ripples from two stones tossed into the same dark pond. Every point along those loops marks galaxies and clusters, billions of suns each. Arranged across distances, light needs billions of years to cross. A structure this size sails so far past the ceiling that the usual excuses run out. Recall the limit, about 1.25 billion light years, the scale past which the universe is supposed to be smooth. The giant ring exceeds even the older, generous estimates of that smoothness scale by a wide margin. It belongs to a class astronomers now call ultra-large structures, objects so big they sit in territory. The standard model says should be empty of anything organized. The scientists studying it laid out the questions it forces upon us, and each one bites. Are structures like this somehow seeded into the universe's very first moments, printed into the initial conditions before galaxies even existed? These giant rings are not expected to be held together by their own gravity, so if gravity did not build them, what did? How do such shapes come to be at all? And how many more of them are hiding out there, waiting in data we have not yet gathered? The researcher was careful, as good scientists are. These structures push against the assumption of smoothness, she and her colleagues wrote, and they invite us to rethink what the scale of smoothness even means. Maybe the ceiling is higher than we thought. Maybe the rule bends in ways we have not worked out. Or maybe the rule is simply failing, and the universe is lumpy on scales it was never supposed to be. What unsettles astronomers most is the clustering of it all. Arc, ring, and now giant ring. 3 record breakers, folded together in a single region of sky. That is either an extraordinary run of luck or a sign that our fair sample of the universe is not so fair after all. And these 3 are not the only giants written across the heavens. In a different part of the sky, a separate team found a ring even larger, and they drew its shape not from quasars, but from the death cries of exploding stars. This other ring was mapped by catastrophe, drawn across the sky by the most violent explosions in the universe. When certain massive stars die, they detonate in bursts of energy called gamma-ray bursts, flashes so bright that for a few seconds, a single dying star can outshine an entire galaxy. These bursts are visible clear across the cosmos, brief and blinding, like flashbulbs going off in the deep dark. Because they are so bright, gamma-ray bursts make excellent markers. Each one pinpoints a spot where a giant star lived and died, and by measuring how far away each burst sits, astronomers can place it on a 3-dimensional map. A separate team collected these death flashes and noticed that a group of them, 9 bursts in one region of sky, did not scatter randomly. They lined up into a ring. The size of this ring is staggering, even next to the others. It spans about 5 billion light years across. Set that beside the ceiling of roughly 1.25 billion, and this ring is around 5 times over the limit. One of the largest regular shapes ever reported in the entire observable universe. 9 exploding stars, spread across billions of light years, arranged into a near circle, like 9 distant fireworks that happened to burst along the rim of an invisible wheel. Here is why using gamma-ray bursts matters so much. The giant arc and the big ring were found through quasar light, one clever method with its own quirks and possible biases. If every oversized structure came from that single technique, a skeptic could argue the technique itself was manufacturing false shapes. But the gamma-ray burst ring comes from a completely different method, a different kind of object, a different team, a different corner of the sky. When 2 separate approaches both keep finding structures too big to exist, the case grows much harder to blame on any one tool. The team behind it said as much. According to the cosmological principle, the universe on the largest scale should be smooth and the same in every direction. Yet the real sky shows complex structures even on enormous scales. Recent discoveries of shapes far exceeding the smoothness limit, they wrote, pose a real challenge to that principle. Their gamma-ray burst ring was, at the time, the largest regular formation known, stretching about 5 times past the scale where uniformity should rule. Now step back and count what has piled up. Walls brushing the ceiling, the giant arc nearly 3 times over, the big ring, a coil where no loop should form, the giant ring, folding arc and ring into one monster, and now a separate ring, mapped by dying stars, 5 times too large. Each found by careful people using careful methods, each supposedly a rarity that should almost never appear. Together they form a chorus, and the chorus is singing that the universe may be lumpy on scales. It was forbidden to be lumpy. So we arrive at the hard question the whole journey has been building toward. What does it actually mean if these structures are real? Not just surprising, but real, confirmed, unmovable. The answer reaches down to the foundation of everything we think we know about the shape and fate of the cosmos. To feel why these giants terrify cosmologists, imagine the standard model of the universe as a house of cards, tall and elegant, every card resting on the ones beneath it. Near the bottom of that tower sits one card holding much of the weight, the assumption that matter is spread smoothly on the largest scale. Pull that card, and you do not lose one card. You risk the whole tower. The big ring counts as roughly the 7th large structure discovered that contradicts the idea of smooth, evenly spread matter. 7 and more have joined the list since. Each one is supposedly so rare it should not appear even once in all of observable space, yet our maps keep turning them up. When impossible things keep happening, the honest conclusion is that they were never truly impossible. Our rule about what can exist was wrong. Here is what actually breaks if the rule fails. Nearly every calculation in cosmology assumes the universe is uniform when you zoom out far enough. That single assumption lets scientists treat the whole cosmos as one simple, even thing and write equations that describe how it expands, how old it is, and how it will end. One physicist put the danger bluntly. Without the assumption of smoothness, he said, all order would break loose. The tidy equations stop being trustworthy. The numbers we quote for the age and expansion of the universe rest on the very smoothness these structures seem to violate. There is a second, sharper wound. Remember that the size limit is really a time limit. Gravity has had about 13.5 billion years to gather matter, and it builds only so fast. A structure billions of light years across, organized into a clean arc or a closed ring, may need more time to assemble than the universe has existed. If these giants are real and were built by ordinary gravity, then either the universe is older than we think, or gravity behaves differently on the largest scales, or some force we have never named lent a hand. Every one of those options rewrites a chapter of physics. That is why these findings are treated as a genuine crisis and not a fun curiosity. This is the second most trusted assumption in all of cosmology, sitting just behind the theory of gravity itself. Shaking it means questioning the ground beneath decades of work. Scientists do not enjoy that. A working model that explains so much is precious, and no one abandons it lightly, nor should they. Which is exactly why the debate is so fierce and so healthy. Some researchers argue the crisis is real, that the structures are telling us the model is cracked and something new is needed. Others insist the model is fine and the structures are misunderstood, either measuring errors or rare flukes we are misreading. Both camps are doing their jobs. The universe does not care which side is right, and the only way to settle it is more evidence, gathered more carefully. For now, the tower of cards stands, but it is swaying, and everyone in the room is watching that one card near the bottom. Whether it holds may decide the shape of physics for the next century. Yet the largest structures are only half of the trouble James Webb has stirred up. The other half is not about things too big. It is about things too old, too grown up, appearing far earlier than any of them should. And the first of these is a single galaxy that seems to have skipped its entire childhood. The galaxy that broke the timeline should not have had time to grow at all. James Webb found it deep in the young universe, its light showing us the cosmos as it looked only about 800 million years after the Big Bang. In cosmic terms, that is infancy. The universe was barely out of the cradle, a small fraction of its current age of 13.5 billion years. Nothing large and finished was supposed to exist yet. Yet there it sat, a galaxy already massive, already crammed with stars, looking for all the world like a mature adult in a room full of newborns. To understand why that stunned astronomers, you need the standard story of how galaxies are supposed to grow and how slow that growth is meant to be. In the accepted model, galaxies build themselves gradually, like a snowball rolling downhill gathering size. The early universe held only faint clumps of dark matter, invisible scaffolding that pulled in gas. Gas cooled and sparked the first small stars. Little galaxies formed, then bumped into one another and merged, slowly stacking up into larger ones over billions of years. Growth is patient. A galaxy the size of ours takes a very long time to assemble, feeding and merging across the long ages of cosmic history. This galaxy skipped the patience. In its first few 100 million years, it had already gathered a giant population of stars, then done something even stranger. It stopped. After a furious burst of star formation, it went quiet, its star-making shut off, leaving a fully grown galaxy sitting still in the middle of the young universe. It is like discovering a person who sprinted from birth to full adulthood in a handful of years, then abruptly stopped aging, standing finished, while everyone around them is still an infant. Think of it this way: if galaxies grow like children, slowly reaching adult size over a long childhood, this one looks like a toddler with the body of a grown athlete. The muscles are already there. The frame is complete, but there simply was not enough time in the universe yet for any normal childhood to have produced it. The clock had not run long enough. The team that studied it did not soften their language. A galaxy this massive, this early, poses a significant challenge to the standard model of how structure forms. The problem is not only its size, it is the speed. To grow this big, this fast, it would have needed to gather and forge stars far quicker than the gentle, merging, snowball model allows. Something sped the process up in a way current theory struggles to explain. And there is a deeper wrinkle. In the standard picture, galaxies need enough of that invisible dark matter scaffolding built up first to pull the gas together and seed their growth. This galaxy seems to have formed before enough of that scaffolding should have been in place. It grew, in a sense, without the foundation it was supposed to require, like a skyscraper standing tall with no record of anyone laying its base. One oddball galaxy might be excused as a rare exception, a lucky early bloomer, but astronomers were about to learn this was not a lonely case. It was the first sighting of a whole crowd of impossibly grown-up galaxies, and the next one held even more stars, and an even deeper mystery about what was missing from its birth. The next galaxy carried a puzzle hidden inside its very substance. Like the first, it appeared impossibly early and impossibly grown, packed with more stars than our own Milky Way despite forming when the universe was still an infant. Our galaxy holds a few 100 billion stars, gathered over more than 13 billion years. This ancient one had assembled a comparable horde in a tiny sliver of that time. The size alone was a shock. What lay underneath was worse. To see the problem, return to the role of dark matter in the standard story. Dark matter is the invisible glue of the cosmos, a mysterious substance that does not shine or reflect light, yet outweighs all the ordinary matter we can see by a wide margin. We cannot look at it directly. We know it is there because its gravity tugs on stars and galaxies, holding them together in ways visible matter alone cannot explain. In the accepted picture, dark matter comes first. It gathers into invisible clumps, and those clumps act like seeds, their gravity reeling in gas that then cools and forms stars. No dark matter seed, no galaxy. This early giant appears to break that order. By the reckoning of the researchers, it grew so large, so fast, that there could not have been enough dark matter built up yet to seed it in the normal way. The scaffolding that is supposed to come first simply had not had time to assemble in the amount required. Somehow, the galaxy pulled together a Milky Way's worth of stars without the invisible foundation the model insists it needs. It is like finding a great cathedral standing complete, with no sign anyone ever poured the foundation beneath it. The team called it what it was, a significant challenge to the standard model of cosmology, echoing the alarm raised by the first galaxy, but pushing it further. This one questioned not just how fast galaxies grow, but the deep assumption that dark matter always leads and ordinary matter follows. Take that away, and a load-bearing piece of the story of how the first structures formed comes loose. And this galaxy did the same eerie thing as the first. After a violent early burst of star-making, it went quiet. It became what astronomers call quiescent, its furnaces of star birth shutting down, leaving a massive finished galaxy sitting still in an era when everything was supposed to be small, wild, and still under construction. Two mysteries in one. It should not have grown so fast, and it should not have stopped so soon. Much like the first discovery, and like others Webb has since turned up, this galaxy threatens to upend our understanding of how the earliest matter came together. Not one strange object, but a pattern of them, each an adult in a nursery, each missing the slow childhood the model demands. The excuse of bad luck gets thinner with every new find. The pattern kept growing. As James Webb swept deeper into the young universe, it did not find one or two early bloomers. It found a whole parade of them, galaxies, blazing far brighter and appearing far earlier than the model ever predicted. A chasm opening between theory and the sky. And the deeper the telescope looked, the wider that gap became. Drop back to the young universe and look around. Before James Webb, the rulebook was clear. The first galaxies were supposed to be small, dim, and rare, faint smudges struggling to switch on their first stars. Astronomers expected the deep sky to be nearly dark, holding only a scattered few of these weak newborns. Finding a bright galaxy far out there was meant to be extraordinarily hard, a needle buried in a haystack of shadow. Webb opened its eye and found floodlights. Galaxy after galaxy blazed in the early cosmos, far brighter and far more numerous than anyone had dared predict. Where the models promised a handful of dim campfires, the telescope revealed a sky studded with lamps already burning fiercely and burning early. One survey mapping the young universe turned up close to 10 times more early galaxies than the standard story allowed. The count alone was a shock. Picture arriving at a stadium an hour before the game, expecting empty seats and a dark field, only to find the lights already on and the stands half full of fans. That is the feeling astronomers had staring into the early universe. The party had started long before the invitations were supposed to go out. These galaxies were not faint or struggling. Many shone with the fury of intense, rapid star formation, forging suns at a pace the gentle old model never accounted for. The problem is confirmed and repeatable. Different teams, using different patches of sky, keep finding the same thing. An early universe far more crowded and far more luminous than predicted. This is real observation, not a single lucky snapshot. What remains unsettled is the cause. Why did so many galaxies light up so soon, so brightly? On that, scientists openly admit they are stumped, and the honest ones call it a growing crisis rather than a solved puzzle. Each of these galaxies pushes on the same tender spot. Building a bright galaxy takes gas, gravity, and time to gather stars in huge numbers. The early universe offered very little time. To shine this brightly this soon, these galaxies had to assemble faster than the model says gravity can work. It is the same time trouble we met with the giant structures, wearing a different costume, too much light, too soon, in a cosmos that had barely begun. The more Webb looked, the wider the gap grew between what theory promised and what the sky delivered. And the deeper it pushed toward the very edge of the observable universe, the stranger the objects became, until it reached one that sits farther away than anything humans have ever seen. A galaxy whose light has traveled almost the entire age of the universe to reach us. That most distant galaxy did more than break the distance record. When astronomers studied it, they found something about its makeup that made no sense for an object born so close to the beginning of time. This galaxy holds the record for the farthest thing ever detected. Its light left home when the universe was younger than 300 million years old, a mere sliver of its current age of 13.5 billion years. That light then traveled for over 13 billion years to land in Webb's detectors. Looking at it is like reading a letter written in the first days of a long life, only now arriving in the mail. By every expectation, an object this early should be crude and unfinished, a rough first draft of a galaxy. What Webb found was the opposite. This galaxy is brighter, more compact, and more chemically rich than anything the models predicted for such an ancient moment. The lead scientist put it plainly. "With Webb, we can see farther than humans ever have," he said, "and it looks nothing like what we predicted, which is both thrilling and troubling. The deepest surprise hides in its chemistry. When the universe was born, it held almost nothing except the two lightest, simplest ingredients, hydrogen and helium. Every heavier element, the carbon in your body, the iron in your blood, the oxygen you breathe, had to be forged later, cooked inside stars and flung out when those stars died. Building up heavier elements takes generations of stars living and dying, each generation seeding the next. That process is slow. It needs time. Yet this ancient galaxy is already enriched with heavier elements, including a surprising amount of nitrogen. That should be nearly impossible so early. It suggests that massive stars formed, blazed, and died in rapid succession, seeding the galaxy with heavy elements at a furious pace, far quicker than the standard timeline allows. It is like opening a brand new bakery in the morning and finding the shelves already stocked with bread that takes all day to bake. Think of the whole young universe as a kitchen that has just been switched on. The ingredients for anything complicated, the flour, the sugar, the spice, have to be made from scratch, and making them takes hours. This galaxy shows up in the first minutes with a finished, spiced cake already cooling on the counter. Someone, somehow, cooked faster than the clock should permit. A co-author of the study named the wound directly. "There is a growing chasm," he said, "between theory and observation in the early universe, and it raises hard questions we now have to face. This one galaxy is a headline example, sitting at the very frontier of the visible cosmos, refusing to look as young as it truly is." Astronomers keep adding objects like this to a lengthening list of early bloomers that break the model. Each new find widens the chasm a little more, and while cataloguing these distant galaxies, Webb kept turning up other specks in the deep sky, tiny points of red light that were even harder to classify. They were so small, so red, and so plentiful that scientists could not agree on what they even were. Some began to wonder if these little red dots were galaxies at all, or something the universe had never shown us before. They are called the little red dots, and the name is exactly as plain as the objects are puzzling. Scattered across Webb's images of the early universe are countless tiny points of deep red light, compact and glowing, appearing in numbers no one expected. When astronomers first tallied them, the sheer count was startling. These dots are everywhere in the young cosmos, far too common to ignore and far too strange to easily explain. Two things make them baffling. First, they are extremely small. The light is squeezed into a point far more compact than a normal galaxy, which usually spreads its glow across a broad disk of stars. Second, they are very red, and in astronomy, red often means either very far away, very dusty, or both. Put those together, and you have objects that are tiny, distant, reddened, and shockingly numerous, a combination that fits nothing in the standard catalogue. The obvious first guess was that they were simply small galaxies packed tightly with stars. Run the numbers, though, and that idea strains. To shine this brightly from such a compact point, a galaxy would need to cram an unbelievable number of stars into a space far too small, packing suns shoulder to shoulder more densely than any known galaxy manages. It would be like fitting the entire population of a country into a single city block, possible to imagine, hard to believe. So astronomers split into camps. Maybe the dots are dense knots of stars after all, crammed together in the chaotic early universe. Maybe they are something stranger, glowing from a hidden engine rather than starlight alone. The disagreement is real and ongoing, a genuine open mystery rather than a settled fact. When scientists cannot even agree on what kind of thing they are looking at, you know the universe has handed them a fresh puzzle. Here is a comparison to hold the strangeness. Imagine walking through a dark field at night and seeing hundreds of small red lights hovering all around, all the same color, all the same size, none of them matching any animal, plant, or lamp you know. You would not just wonder where they came from, you would wonder what they are. That is roughly where astronomers stand with the little red dots. They can measure them, count them, and map them, yet they cannot confidently name them. What makes the dots more than a curiosity is what they might be hiding. If they are not simply clusters of stars, then something else is powering that intense red glow from such a tiny space. And in the universe, when a huge amount of light pours out of a point far too small to hold that many stars, one suspect always rises to the top of the list. The most daring explanation says these dots are not really galaxies at all. Each one might be a cloak wrapped around a monster, a giant black hole feeding in secret. And if that is true, it points to a fresh impossibility about how fast the darkest objects in the universe grew up. The wild idea has an unforgettable name: black hole stars. The thought goes like this: each little red dot might hide a supermassive black hole at its center, a giant many millions of times the mass of our sun, buried inside a thick cocoon of gas. As the black hole devours the gas around it, the swirling material heats up and blazes with light. From far away, that glowing cocoon looks like a single point, small and red, disguised as a star or a tiny galaxy. To understand why this is so strange, you need to know how black holes are supposed to grow. A black hole is a place where gravity pulls so hard that nothing escapes, not even light. Black holes get bigger by swallowing matter, gas, dust, and shredded stars. That feeding has a natural speed limit because a feeding black hole shines fiercely, and its own glow pushes back on the very gas trying to fall in. So growing a truly giant black hole is supposed to take a very long time, billions of years of patient, limited feeding. The little red dots refuse to wait. If they really are giant black holes cloaked in gas, then supermassive black holes existed when the universe was very young, far too early for them to have grown so large through normal, slow feeding. Webb has separately found other signs of the same trouble: giant black holes appearing not long after the Big Bang, before they should have had time to bulk up. The black hole star idea would mean these monsters are even more common in the early universe than anyone guessed. Picture a sumo wrestler weighing hundreds of pounds. Now imagine finding a baby, only weeks old, already that size and that heavy. You would not just be surprised, you would demand to know how, because no normal growth could get there in the time available. A giant black hole in the infant universe is that impossible baby. The black hole star explanation tries to account for it by hiding the monster inside a glowing shroud of gas, which might let it grow in ways the simple limits do not fully cover. The idea is bold and far from proven. Some scientists find it exciting, a fresh answer that ties together the red dots and the early black hole puzzle in one stroke. Others are cautious, warning that a wild explanation needs wild evidence before anyone accepts it. That caution is exactly right. This sits firmly in the territory of daring theory, not confirmed fact, a a possible answer still fighting for its life. Whether the dots are dense star clusters or cloaked black holes, they carry the same message as everything else Webb has shown us. The early universe built big, bright, heavy things faster than our theories say it could. Structure, light, and gravity all ran ahead of schedule, and that early rushing is not confined to single objects. When astronomers zoomed back out to the largest scales, Webb showed them the young cosmic web already strung together, and one strand of it was so massive and so packed that it dwarfed anything they thought could exist so soon. Webb aimed at the deep universe and traced a single strand of the cosmic web that left astronomers reeling. This one filament, a bridge of galaxies and clusters running through space, carries something like 100 times the mass of our entire Milky Way galaxy. Remember, the Milky Way already holds a few 100 billion stars. Now imagine a chain packing the weight of 100 such galaxies, strung together into one enormous thread stretching across the cosmos. The trouble is not only its size, it is how tightly the galaxies are grouped and how early. Webb used its infrared eyes to study the makeup of this filament and found a densely packed sequence of galaxies and clusters, far more crowded than the standard picture expects for that part of the young universe. Matter had gathered along this strand in numbers that outrun the model, herded into a single dense highway of galaxies when the cosmos was still supposed to be sparse and unfinished. Filaments like this are the largest known structures in the universe, the main girders of the cosmic web. Along these strands, matter piles up and slowly flows, feeding the great clusters that form where filaments cross. So finding one this massive and this packed matters. It hints that the web assembled faster and denser than we thought, adding yet another entry to the long list of things that grew up too soon. Picture the difference between a quiet country lane and a 12-lane superhighway jammed bumper to bumper with traffic. The standard model expected the early cosmic web to be more like scattered country lanes, thin and lightly traveled. This filament looks like the packed superhighway, dense with galaxies rushing along a shared route. Building that much traffic that early is hard to square with a universe that is supposed to still be waking up. A discovery like this ripples outward into the deepest questions in cosmology. If filaments this massive existed so early, what does that say about how quickly matter clumped, and about the invisible dark matter that is supposed to guide that clumping? It presses on the same tender points as the giant galaxies, only written at a far larger scale, in the very architecture of the universe, rather than in single objects. The filament also reminds us that the cosmic web is a living, moving thing. These strands are highways, where matter is on the move, flowing toward the busy junctions where galaxies gather thickest. That flow is the secret engine behind how galaxies grow and how the web itself takes shape over cosmic time. To picture how the whole web feeds itself and why matter ends up so unevenly spread, with dense highways here and vast emptiness there, you have to follow the flow. You have to watch how gas and dark matter travel along these invisible rivers, pooling into galaxies and clusters, draining the spaces in between until they run nearly dry. The cosmic web works like a landscape carved by invisible rivers. Along every filament, gas and dark matter do not sit still. They flow, streaming slowly along the strands toward the dense knots where galaxies cluster thickest. Think of the filaments as riverbeds, and the great galaxy clusters as the seas those rivers empty into. Over billions of years, matter drifts downhill along these channels, gathering where the flow collects. Galaxies grow by drinking from these rivers. A young galaxy sitting along a filament is fed by streams of cool gas flowing in from the strand, raw fuel for building new stars. The more richly a galaxy is fed, the faster it forms stars and swells in size. The busiest galaxies live at the junctions where several filaments meet, because that is where the most matter pools, like a city built where many rivers join and trade flows in from every direction. This flowing explains why the universe looks so lumpy on smaller scales. Matter does not spread evenly. It drains out of the empty regions and piles into the strands and knots. The way water on a tilted table runs into cracks and puddles instead of coating the surface flat. Over time, the rivers rob the empty spaces to feed the crowded ones, deepening the difference between the packed highways and the barren gaps. Here is a way to feel it. Imagine a giant sheet of glass sprinkled evenly with water droplets. Tilt and shake it gently, and the droplets start to run together, streaming into thin lines, then pooling where the lines cross, leaving wide, dry patches behind. The water was once spread smooth. Now it hangs in threads and beads with emptiness between. The cosmic web, formed by a slow version of that same gathering, gravity pulling matter into strands and knots over the whole age of the universe. Dark matter leads this dance. Being far more plentiful than ordinary matter and feeling only gravity, it clumped first and laid down the invisible riverbeds. Ordinary gas then followed those channels, sliding into the dark matter's grip and lighting up as stars and galaxies. So, the glowing web we finally photographed traces a deeper, darker web underneath, the true skeleton along which everything else was strung. This flowing picture is one of the great successes of modern cosmology. It explains, in broad strokes, how a nearly smooth young universe grew into the strands, clusters, and galaxies we see. It also explains why some regions ended up crowded while others emptied out. The rivers giveth, and the rivers taketh away. But every river system leaves something behind. Between the strands, where the flow has drained away almost everything, lie the vast, empty basins of the cosmos. They are the largest features of the web by sheer volume, and they are so profoundly empty that they force us to rethink what emptiness even means. Some of these voids are so enormous and so barren that a galaxy trapped inside one would drift for the whole age of the universe without ever meeting a neighbor. The voids are the great deserts of the universe, and their emptiness is almost impossible to overstate. These are enormous rounded regions between the filaments where matter has drained away, leaving vast bubbles of near nothing. A single void can stretch across hundreds of millions of light years, a hollow so wide that light itself, the fastest thing there is, needs 100 million years or more to cross from one side to the other. Inside a void, galaxies are painfully rare. While the filaments and clusters teem with galaxies packed close together, a void might hold only a scattered few, drifting far apart in the dark. Imagine the crowded strands as brightly lit cities, and the voids as endless stretches of empty ocean between them, where you can sail for a lifetime and never sight land. Consider what the night sky would look like from a planet deep inside a void. From Earth, we are lucky. We sit in a busy neighborhood, surrounded by countless galaxies whose light fills our long exposure photographs. From within a great void, the sky would be far lonelier. The nearest other galaxies would lie so far away that they would be faint or invisible, and for much of human history, astronomers on such a world might have believed their galaxy was the only one in existence. Voids are not perfectly empty, and that matters. They still contain thin wisps of gas and faint threads of dark matter, and the rare galaxies inside them tend to be small and quiet, starved of the rich rivers of matter that feed galaxies in the crowded strands. A void galaxy grows up hungry, cut off from the busy highways, developing slowly in near isolation. Studying these lonely galaxies teaches us how much a galaxy's fate depends on where in the web it happens to live. The existence of huge voids is another sign of just how uneven the universe is on medium scales. The cosmic web is a story of extremes, dense strands and clusters on one side, colossal empty basins on the other. Only when you zoom out to the very largest scale, past the strands and the voids alike, is the universe supposed to average out into smoothness. That is the promise of the cosmological principle. Below that scale, extremes rule, and the voids are among the most extreme features of all. To picture the balance, imagine a stiff bath sponge. It is mostly holes, wide empty pockets, with only thin walls of material threading between them. The universe on large scales looks much the same, a foam of giant empty bubbles separated by thin sheets and strands of galaxies. The voids are the holes in the cosmic sponge, and they take up most of the volume of space. Most voids, while staggering, still fit within what the models can handle. But astronomers have found at least one emptiness so gigantic, so far beyond a normal void, that it strains explanation. A hole in the cosmos, hundreds of millions of light years across, where almost nothing exists at all. Some have taken to calling it the Great Nothing, and its sheer scale of emptiness raises the same haunting question as the giant structures, in reverse. How did the universe carve a hole so big? At the far extreme of emptiness sits a region so vast and so barren that it has earned nicknames like the Great Nothing. This is a supervoid, a hole in the cosmic sponge far larger than an ordinary one, stretching across a truly staggering span of space where galaxies are scarce almost to the point of absence. It is emptiness on a scale that even seasoned astronomers find hard to accept. What makes a supervoid so troubling is the same trouble the giant structures raise, only flipped upside down. The cosmological principle promises that on the largest scales, matter should spread out evenly, with no feature too big or too extreme. A giant structure breaks that promise by being too crowded. A supervoid breaks it from the other side by being too empty. Both are the kind of oversized feature the smooth universe was not supposed to allow. Some astronomers have linked the largest known emptiness to a strange cold patch seen in the faint afterglow of the Big Bang, a spot in the earliest light of the universe that looks colder than its surroundings. One idea suggests that light passing through such an enormous void loses a tiny bit of energy on its long journey, arriving to us slightly chilled. If that connection holds, the supervoid would leave a fingerprint stamped on the oldest light in existence. The link is debated and unproven, an intriguing possibility rather than a settled case. Try to grasp the emptiness with a comparison. Imagine the busiest city on Earth, streets packed shoulder to shoulder with people. That is a galaxy cluster. Now imagine the emptiest desert, where you could walk for weeks and never see another soul. That is a normal void. A supervoid is emptier still, as if you could travel for years across that desert, faster than any rocket, and never once pass a living thing. The scale of the nothing is the whole point. How does a universe carve such a hole? In the normal picture, voids grow slowly as gravity drains matter out of them into the surrounding strands over billions of years. A supervoid would require that draining to have worked with unusual thoroughness, or would need a very large empty region baked in from the beginning. Building an emptiness this extreme, like building a structure this large, pushes against the limits of how uneven the universe is allowed to be. So the giant structures and the giant voids tell two halves of one story. On one side, arcs and rings and packed filaments, too much matter gathered too tightly. On the other, supervoids, too much emptiness carved too deep. In a truly smooth universe, neither extreme should reach the sizes we keep finding. Yet, we keep finding both. Step back from all of it. The impossible early galaxies, the packed filaments, the arcs and rings, the yawning voids, and a single theme emerges from every direction. Across scales large and small, the universe seems to have built its structure faster, bigger, and more sharply than our best theory says it possibly could. That single theme, that the cosmos did too much too soon, may be the deepest clue of all, and it points straight at the two invisible ingredients that secretly rule everything we see. Gather every strange discovery into one pile, and a single pattern stares back. The universe did too much, too soon. The giant galaxies grew up before they should have. The bright early galaxies switched on ahead of schedule. The massive filaments packed together too early. The arcs and rings assembled at sizes that need more time than the cosmos has existed. Different objects, different scales, one shared message. Structure ran ahead of the clock. This is why so many scientists now speak of a growing chasm between theory and observation in the early universe. The standard model is a patient story. It says structure forms slowly, gravity gathering matter step by careful step across billions of years. Webb keeps showing us a universe that skipped ahead, arriving at maturity, size, and organization far quicker than patience allows. The theory describes a slow river. The sky keeps showing a flash flood. Here is why time sits at the very heart of the problem. Everything in the universe was built by gravity pulling matter together, and gravity works at a limited pace. The universe is about 13.5 billion years old, and that is all the time gravity has had. To build something, gravity needs enough of two things: matter to pull and time to pull it. Run short on either, and the structure should not exist. Again and again, Webb shows us structures that seem to have beaten the clock. Picture a builder given a fixed number of days to raise a city. The standard model calculates how much that builder could finish in the time allowed. A few foundations, some early walls, nothing grand. Then we look at the early universe and find finished towers, packed neighborhoods, and sprawling highways already standing. Either the builder worked impossibly fast, or there was more help than we counted, or our calendar of how much time passed is wrong. Every one of those answers rewrites part of physics. So, the question sharpens. What could let the universe build so much, so fast? The suspects are the two great invisible forces that dominate the cosmos, the ones we can measure by their effects yet have never truly seen. Together, they make up the overwhelming majority of everything, dwarfing the ordinary matter of stars, planets, and people. If the early universe cheated the clock, one of these hidden ingredients is the most likely culprit. The first is a substance, an invisible mass that provides the gravity to gather structure. The second is a force, a mysterious push driving the universe to expand faster and faster, working against the gathering. Structure formation is a tug of war between them, one pulling matter together, the other stretching it apart. Get the balance of these two wrong, and the whole timeline of the universe shifts. Our theories rest on specific assumptions about how much of each exists and how each behaves. If Webb's discoveries are telling us the universe built structure faster than expected, the simplest suspect is the invisible mass that does the building. The substance whose gravity is supposed to seed every galaxy and every strand of the web. We cannot see it, we cannot touch it. Yet without it, by the standard story, none of us would be here. And the early universe is beginning to hint that this invisible glue may not be behaving the way we always believed. The invisible mass is called dark matter, and it is the strangest thing holding the universe together. We cannot see it, because it gives off no light of any kind, not visible, not infrared, nothing. We cannot touch it, because it barely interacts with ordinary matter at all. It could be streaming through your body right now by the billions of particles, and you would never feel a thing. Yet by the standard model, this ghostly substance vastly outweighs all the ordinary matter in the universe, all the stars, planets, gas, and people combined. How do we know it is there if it hides so well? By its gravity, galaxies spin far too fast to hold together with only the matter we can see. Their visible stars alone do not have enough gravity to keep the galaxy from flying apart. Yet they do not fly apart. Something invisible must be gripping them, providing extra gravity. Scientists call that something dark matter, and its fingerprints show up everywhere, in spinning galaxies, in the way galaxy clusters bend light, in the very shape of the cosmic web. In the standard story, dark matter is the master builder of everything. Because it is so plentiful and feels only gravity, it clumped together first in the early universe, forming invisible scaffolding. That scaffolding then pulled in ordinary gas, which cooled and lit up as stars and galaxies. No dark matter, no scaffolding, no galaxies. It is the hidden frame on which all visible structure was hung. Now recall the trouble Webb keeps raising. Some early galaxies appear to have grown huge before enough dark matter scaffolding should have been in place to build them. Others formed and shut down with a speed the scaffolding model struggles to explain. If dark matter really does lead the way, these galaxies arrived before their leader. It is like finding houses standing on a lot where the foundation was never poured or poured far too late. The plot only thickens. Webb has turned up hints that dark matter might play surprising roles we never fully accounted for. Some researchers suggest dark matter could have helped forge the earliest giant black holes, seeding them faster than ordinary processes allow. Others propose that the very first stars might have drawn heat from dark matter itself, burning in a way unlike any star today. These ideas are speculative, still being tested, but they share a theme. Dark matter may be doing more, and doing it differently than our tidy model assumes. Think of dark matter as the invisible glue in a model kit. The standard instructions say exactly how much glue to use and where, and how long it takes to set. Webb keeps showing us finished models that set faster than the glue should allow, or that hold together in spots where the instructions say no glue was applied yet. Either we are misreading the instructions, or the glue is not the glue we think it is. Dark matter is only half of the invisible universe. The other half is not a substance that pulls things together. It is a force that shoves everything apart, growing stronger as the universe ages, and it makes building giant structures even harder to explain, because this force is stretching space itself, and it has been winning the tug-of-war for billions of years. The opposing force is called dark energy, and it is the great pusher of the cosmos. While dark matter's gravity pulls matter together, dark energy does the reverse. It drives space itself to expand, pushing everything apart, and stranger still, it makes the expansion speed up over time. The universe is not just growing, it is growing faster and faster, and dark energy is the reason. We discovered this by watching distant exploding stars and measuring how quickly galaxies rush away from us. The farther out astronomers looked, the more they realized the expansion was accelerating, as if an invisible force were stepping on the gas pedal of the universe. Dark energy is our name for whatever that force is, and like dark matter, we can measure its effects clearly, while understanding its true nature almost not at all. It makes up the largest share of everything in the cosmos, yet remains a near total mystery. Dark energy turns the growth of structure into a tug-of-war. On one side, gravity, powered by dark matter, works to pull matter together into galaxies, clusters, and the cosmic web. On the other side, dark energy stretches space and tries to pull everything apart. For the first stretch of cosmic history, gravity had the upper hand, and structure grew. As the universe expanded and thinned out, dark energy gradually took over, and now it dominates, slowly winning the war and pushing the great structures away from one another. This makes the giant structures even harder to explain. Building an arc or a ring billions of light years across requires gravity to gather matter over enormous distances. But dark energy is actively fighting that gathering, stretching the very space the matter would have to cross. It is like trying to build a long sandcastle on a beach that keeps stretching wider beneath your hands. The bigger the structure you want, the more the expanding ground works against you. To assemble a coherent giant across billions of light years, gravity had to win a battle that dark energy was busy trying to lose for it. So the two invisible forces set the stage for everything, and the timeline of the universe depends on getting their balance exactly right. Too much dark matter and structure would clump too fast. Too much dark energy, and it could never clump at all. Our standard model picks specific amounts of each that are supposed to match what we see. Webb's discoveries of early, oversized structure suggest the balance in our model may be off, tilted somehow toward building faster and bigger than the equations predict. That is the deep discomfort running under all these findings. The universe seems to have gathered structure more powerfully than a cosmos ruled by our version of these two forces should manage, gathering it early, gathering it large, gathering it against the growing push of expansion. At this point, the case for a crisis in cosmology sounds overwhelming. Yet good science does not celebrate a crisis. It attacks it, hunting for boring explanations before reaching for revolutionary ones. And a group of skeptical scientists decided to test whether the most famous giant structure of all might be far less impossible than everyone feared. They ran the universe on a computer again and again to see if these monsters could appear by pure chance. The best science tries hardest to destroy its own most exciting ideas, and that is exactly what a team of skeptical researchers set out to do. Before accepting that the giant arc shattered the rules of the cosmos, they asked a simple, deflating question. What if a structure that big could show up by chance, even in a perfectly smooth, rule-abiding universe? To find out, they built universes inside a computer and went looking. Their tool was the cosmological simulation, a way of recreating the universe's growth inside a powerful machine. Scientists load in the starting conditions, the faint ripples of the early cosmos, the amounts of dark matter and dark energy, the laws of gravity, then let the simulated universe evolve across billions of years of computed time. Out comes a virtual cosmos, complete with its own filaments, clusters, and voids, all obeying the standard model perfectly. Crucially, these simulated universes are built to be smooth on the largest scales, exactly as the cosmological principle demands. Then the team went hunting inside their obedient, rule-following universes, searching for structures as large as the giant arc. If the arc truly broke the rules, then a universe that follows the rules should never produce anything like it. But that is where the surprise came. In their simulations, and even in patterns generated at random, structures of similar size to the giant arc did appear. A rule-abiding universe, it turned out, could cough up an arc that big now and then, purely by chance. This is a serious challenge to the crisis story, and it deserves to be taken seriously. The team argued that the giant arc does not necessarily violate the cosmological principle at all, because similar giants showed up in their smooth simulations without any rules being broken. If a lawful universe can produce such structures by luck, then finding one in the real sky is not proof that the laws are wrong. It might just be a rare roll of the cosmic dice. Think of it like flipping a coin 1,000 times. Somewhere in that long string of flips, you will almost certainly find a run of 10 heads in a row. On its own, 10 heads looks shocking, like the coin must be rigged. But given enough flips, such runs are expected, even guaranteed. The skeptics argue the giant arc might be that run of 10 heads, striking to stumble upon, yet fully allowed in a fair game played long enough. The universe offers an enormous number of flips. It is vast, filled with countless galaxies scattered across unimaginable distances. With so much sky and so many objects, the chance that some of them happen to line up into a large, eye-catching shape is not as tiny as it first seems. Rare events become likely when you give them a big enough stage. This does not prove the giant arc is meaningless, and the scientists who found it push back, standing by their discovery. It does inject a healthy dose of doubt, reminding everyone that a striking shape is not automatically a broken law. But how, exactly, can pure randomness fake a smooth, sweeping curve billions of light years long? The answer reveals something unsettling, less about the universe and more about the way we look at it. To see how randomness can fake a giant, start with a handful of scattered dots. Sprinkle points at random across a page, truly random, no pattern intended. Then stare at them. Almost always, your eye will find something. A rough line here, a loose curve there, a cluster that seems meaningful. The dots were placed by chance, yet shapes seem to leap out of them. This is the trap waiting at the heart of the giant structure hunt. The cosmos gives randomness plenty of room to work. Galaxies number in the trillions, scattered across a universe so vast that light has never crossed it. With that many objects spread across that much space, some of them will inevitably fall into arrangements that look organized. A few dozen galaxies happening to line up along a gentle curve is not a miracle when there are trillions of galaxies and countless possible curves to be traced. Given a large enough canvas, chance paints shapes on its own. Now, add the way these structures are found. Astronomers map where matter clumps, then look for patterns in the map. But looking for patterns is a dangerous business, because if you search hard enough through a big enough dataset, you will always find something that stands out. The more shapes you are willing to consider, the more likely one of them shows up by luck alone. A curve, a ring, a wall, all become findable if you scan enough sky with a patient eye. Return to the ring that faced Earth. A ring only looks like a clean ring when viewed face on. That means our methods naturally favor finding face-on rings and mis-tilted ones. So the sky could be full of random clumps, and our pattern-hunting eyes and tools would still pull out the occasional striking ring, precisely because those are the shapes we are best at noticing. The universe hands us random dots. We hand back a ring. Here is the sobering part. This does not prove the giant structures are illusions. It only proves that we cannot trust our eyes or our excitement to tell real structure from lucky coincidence. The only way to know is with cold, careful statistics, calculating exactly how often a smooth, random universe would produce a shape this size. If such shapes are expected by chance, the structure means little. If they are truly, wildly unlikely even given the vastness of space, then it means everything. That is the real battleground of this whole mystery. The two camps are not arguing mainly about what the shapes look like. They are arguing about the odds. Are these giants far too improbable to be chance, signaling broken laws? Or are they rare but allowed flukes, striking to see yet fully permitted in a lawful universe? Careful counting, not gut feeling, will settle it. So the crisis hangs in the balance, suspended between two honest possibilities, new physics or clever coincidence. The evidence is real, the debate is fierce, and the answer is not yet in. Yet suppose the counting comes back and the structures survive, proven too improbable for mere chance. Then we would need something extraordinary to explain them. Some exotic feature of the early universe, powerful enough to seed rings and arcs across billions of light years. And physics has one wild candidate waiting in the wings. If the giant structures turn out to be real, then something exotic must have built them, and one of the strangest suspects is called a cosmic string. These are not strings in any ordinary sense. They are hypothetical flaws in the fabric of space itself, incredibly thin and unimaginably dense, thought to have possibly formed in the first fractions of a second after the Big Bang, when the young universe was cooling at a furious pace. To picture how such flaws might form, think about water freezing into ice. When a pond freezes, it rarely forms one flawless sheet. Instead, cracks and lines of stress appear where different patches of ice meet, frozen defects locked into the surface. Scientists suspect the early universe cooled in a similar way, and as it did, it may have trapped defects into the fabric of space, long, thin lines of concentrated energy. Those trapped lines are cosmic strings. A cosmic string would be astonishing, thinner than an atom, yet so dense that a short length of it could outweigh a mountain, even a planet. Stretched across the young cosmos, such strings would carry enormous gravity along their length, and here is why they matter for our mystery. As a cosmic string moved through the early universe, its powerful gravity could have herded matter along it, seeding galaxies into long lines, sweeping curves, even loops and rings, exactly the kinds of oversized, oddly regular shapes we keep finding. This is why cosmic strings keep coming up whenever astronomers puzzle over the giant arc and the rings. A cosmic string offers a way to build a huge, organized structure quickly, using a feature baked into the universe at its very birth rather than slow gravity working across billions of years. It could explain how a clean curve or a near-perfect ring formed at a scale that ordinary structure building cannot reach in the time available. Even a Nobel Prize-winning physicist named Jim Peebles has floated the idea that cosmic strings might account for some of the stranger patterns in how galaxies are spread across the sky. Set against the clock, the appeal is obvious. Ordinary gravity is slow, and dark energy fights it, So building a billion light-year ring the normal way seems nearly impossible in the time the universe has had. A cosmic string sidesteps that problem. Its intense gravity could shape matter rapidly, planting the seed of a giant structure early, letting galaxies gather along a template that was there almost from the beginning. The template does the hard work the slow universe could not. Honesty demands a warning. Cosmic strings have never been detected. They remain a bold theoretical idea, a possibility allowed by some physics, but never confirmed by any observation. Invoking them to explain the giant structures trades one mystery for another, replacing an unexplained shape with an unproven cause. That is a legitimate move in science, offering a testable hypothesis, but it is a long way from a settled answer. For now, cosmic strings are a fascinating maybe, not a fact. Whether the answer proves to be cosmic strings, a hidden flaw in our understanding, or simple coincidence, the stakes could hardly be higher, because if the giant structures are real, and if the early universe truly built too much too soon, then the standard model of cosmology, the grand story we have trusted for decades, may be facing the biggest reckoning in its history. And that reckoning would reach all the way down to the deepest questions any human can ask. Stand back and take in the full weight of what is at stake. For decades, cosmology has run on one grand story, the standard model, a triumph that explains the age of the universe, its expansion, the glow of its earliest light, and the sweep of the cosmic web. It is one of the most successful ideas in the history of science. Now, a rising tide of discoveries, the giant structures, the impossible early galaxies, the packed filaments, presses against its foundations at once. If enough of them hold up, the grand story faces its biggest reckoning yet. If that happens, cosmology reaches a fork with two roads. Down the first road, the model gets patched. Perhaps the smoothness limit is simply higher than we calculated, and structures can grow larger than we thought while the core theory survives. Perhaps our recipe for how fast galaxies form needs adjusting. These would be real changes, but repairs rather than demolition, keeping the familiar house standing with new beams and stronger walls. Down the second road, the repairs fail, and something deeper must change. Maybe dark matter behaves differently than we assume. Maybe dark energy is not quite the force we think. Maybe gravity itself works differently across the largest scales. Or the early universe unfolded in a way our timeline gets wrong. Any of these would mean rewriting a chapter of physics, replacing part of the story with something new and strange. This road is harder and more frightening, and it is the one that would reshape science for a century. Why should any of this matter to you? Standing on a small planet circling an ordinary star, because the standard model is how we answer the oldest questions our species has ever asked. How did everything begin? How old is it all? How did we come to be here? And how will it end? Every one of those answers rests on this framework. Shake the framework, and you shake our deepest understanding of where we came from and where we are going. There is also a quieter, more human stake. The cosmological principle was born from humility, the hard-won lesson that we occupy no special place in the cosmos. If giant structures break that principle, it does not restore us to the center, but it does mean the universe is stranger and less uniform than we believed, with a texture and a history we have barely begun to read. We would be living in a wilder cosmos than the tidy, smooth one our equations described. None of this is settled, and that is the honest heart of it. The discoveries are real and confirmed. The interpretations are fiercely debated. Some of the finest minds in the field believe we are watching a revolution begin. Others believe the model will survive, bruised but intact, once the statistics are done and the flukes are sorted from the signals. Both could be partly right. Science advances by exactly this kind of open, evidence-driven struggle. What everyone agrees on is that we cannot answer these questions with the maps we have now. We have pushed our current eyes to their limit, and the limit is where the mystery lives. To settle whether the universe truly broke its own rules, we need to see more sky, more sharply, than ever before. and a new generation of telescopes is about to open its eyes and do exactly that. The answer is coming, and it will arrive through a wave of powerful new eyes now turning toward the sky. James Webb cracked the mystery open, but settling it demands surveying far more of the universe than any single telescope has managed. To know whether the giant structures are real or lucky flukes, astronomers need to map millions upon millions of galaxies across huge stretches of sky, then run the cold statistics that separate true signals from chance. The tools to do that are finally coming online. One of the most anticipated is the Nancy Grace Roman Space Telescope, a wide-eyed observatory built for exactly this kind of work, where Webb stares deeply at small patches with incredible sensitivity. This telescope is designed to capture enormous swaths of sky at once, surveying vast numbers of galaxies in a single sweep. Think of Webb as a powerful zoom lens and Roman as a giant wide-angle camera. To test whether oversized structures are truly too common, you need the wide view, the ability to survey huge volumes of space and count how often such giants really appear. Other great observatories are joining the hunt from the ground and from orbit, each mapping galaxies across the sky in staggering numbers, charting the cosmic web in 3 dimensions across billions of light years. Together they will build the largest and most detailed maps of cosmic structure ever made, dwarfing what we have today. With those maps in hand, astronomers can finally calculate with real precision how likely a smooth universe is to produce arcs and rings the size of the ones we have found. That is how this mystery gets solved. Through evidence, not argument. If the giant structures keep appearing in vast new surveys, far more often than a smooth, lawful universe should allow, the case for new physics will grow overwhelming, and the standard model will face its long-feared reckoning. If instead the giants turn out to be rare flukes, expected once you search a big enough sky, then the model will survive, and the arcs and rings will become fascinating curiosities rather than revolution. Either way, we win an answer. We are living in a rare and thrilling moment in science. For most of history, humans could only guess at the shape of the universe on its grandest scales. Now, within our lifetimes, we are building the instruments to actually measure it, to put the deepest assumptions of cosmology to a real test. The generation watching these telescopes come online may be the one that learns whether the universe is smooth and lawful, or wild and lumpy in ways we never imagined. And that is the true gift of the structure James Webb found. It did more than dazzle us with its size. It caught the universe in a place where our best theory might break, and in doing so, it handed us one of the greatest questions a thinking creature can ask. Is the cosmos the orderly, uniform place we assumed, or is it stranger, older, and more surprising than our equations dared to say? Somewhere out there, in the deep dark, a structure larger than we can explain is waiting for us to understand it, and for the first time, we are building the eyes to finally see it clearly. Keep looking up. The answer is almost within reach.